Basically, how do we know if something's a quadratic function? Well, if we recall back to linear functions, well, linear functions can be defined by either f of x equals mx plus b or f of x equals ax plus b. Remember that the highest degree term was degree 1. This was x to the first power and x to the first power here. Well, by definition, a quadratic looks something like this. If a, b, and c are real numbers with a not equal to 0, the quadratic function can be represented by ax squared plus bx plus c. Notice these last two terms look like a linear function, but we added this additional term, this ax squared, out front. This is what's known as the standard form for a quadratic equation, the standard form for a parabola. Well, let's talk about the properties of a quadratic function. We have f of x equals a x squared plus bx plus c. Let's talk about this a. The graph of a parabola, or graph of quadratic formula, forms a parabola. This is a U-shaped graph, and it opens either upward if a is positive or downward if a is negative. In this first example, we have f of x equals x squared minus 1. The coefficient in front of the x squared is understood to be 1, which is positive, and notice this graph makes the U shape opening upward. This next example is f of x is negative x squared plus 2x plus 3. Notice the coefficient of the x squared is negative 1, and this graph opens downward and has the standard U shape. The vertex of a parabola is either the highest point if the parabola opens downward or the lowest point if the parabola opens upward. We look at our two examples. Our f of x equals x squared minus 5. The vertex is the very lowest point on the parabola. In this case, it's 0, negative 5. In our second example, we have f of x is negative x squared plus 2x plus 3. Therefore, we know this parabola faces downward, and so the vertex is the very highest point. And in this case, that point is 1, 4. We have what's called the axis of symmetry, and this is a vertical line which cuts through the vertex, literally splitting the parabola in half to where the two halves are mirror images of themselves. Here's our first example, the f of x equals x squared minus 5. Notice in this case, the vertical line is just the y-axis. And the vertical line, the formula for the vertical line is x equals 0 in this case. It's the x-coordinate of the vertex. In this case, we have another vertical line cutting through this second example. This is the equation x equals 1. Of course, again, we look at the x-coordinate of the vertex. That is the equation for the vertical line. Remember, the equation for all vertical lines are x equals constants. In this case, the constant is 1, and in the case over here, the constant is 0. Now, a also has another property. It controls the width of the parabola. For large values of a, the parabola is very narrow, and for small values of a, the parabola is much wider. Here, the purple graph is the original graph, the f of x equals x squared minus 5. The red graph is simply f of x equals 2x squared. In this case, notice how much narrower the graph is. And finally, the green graph is f of x equals 1/2 x squared minus 5. Again, all of these have pretty much the same formulas. The only difference is the a value that's in front. And again, the smaller the a value, the wider the graph. The larger the a value, the narrower the graph. Alright, let's see an example now applying these. Use the graph of the function below to identify the following: the leading coefficient, the vertex, and the axis of symmetry. This parabola opens downward, so we automatically know the leading coefficient is negative. We know the vertex in this case is the highest point, so if we just find the highest point, that's the point 2, -1. And the axis of symmetry passes through the vertex, so it's x equals, in this case, 2. So we've answered all three of our questions really quickly by knowing the little properties that we do know about a parabola. There's also called what's known the vertex form of a parabola. If the vertex of a parabola is the point h, k, then the vertex can be written, or the parabola can be written as f of x equals a times the quantity x minus h closed quantity squared plus k. Again, if a is greater than 0, then the parabola opens upward. If a is less than 0, the parabola opens downward. Let's talk about what's called completing the square. We want to take this quadratic, it's f of x equals x squared plus 12x plus 5. And write it in vertex form by completing the square. If we start out by replacing the f of x with y, simply because it's easier to write, we have y equals x squared plus 12x plus 5. We're going to get the x's by themselves. So we're going to leave the x squared and the 12x on the right-hand side, and we're going to subtract 5 from both sides. So we get y minus 5 is x squared plus 12x. The next step is actually completing the square. We're going to take this b term, this 12 in front of the x, and we're going to take half of it, so half of 12 is 6, and then we're going to square it. And when we square 6, we get 36. So this gives us x squared plus 12x plus 36 on the right-hand side. And when we simplify on the left-hand side, we're going to get y plus 31. The reason we did this is because the x squared plus 12x plus 36 is now a perfect squared trinomial. And it should factor. In fact, it factors to x plus 6 squared. So we get y equals the quantity x plus 6 squared minus 31. So this form in our final answer is equivalent to what our original equation was. I do want to make one comment when we completed the square. Before we did the half of b, we had to make sure the x squared coefficient was 1. If it wasn't 1, we'd have to divide both sides by that number or factor out that number. And we'll go more into this later as we look at solving quadratic equations. The vertex form and the axis of symmetry. Here is the formula for f of x equals ax squared plus bx plus c. By definition, the axis of symmetry is equal to x equals negative b over 2a. We could derive this through a quadratic equation, which we'll learn later, or through methods of calculus that you'll see in other classes beyond this. But for right now, let's just take it at face value that your axis of symmetry is x equals negative b over 2a. And we know the axis of symmetry is always the x value of the vertex. So there's my x value of my vertex, which is the axis of symmetry. And to get the y value, I have to plug that x value back into my function. So your vertex is always negative b over 2a, comma, f of negative b over 2a. Let's look at an example. Find the vertex of this graph. F of x is 1/2 x squared plus 4x minus 9. My axis of symmetry is negative b over 2a, so negative 4 over 2 times 1/2, which is negative 4. And f of negative 4, when I plug back into this equation, is 1/2 times negative 4 squared plus 4 times negative 4 minus 9, which yields negative 17. So the axis of symmetry was the x value of my vertex. And when I plug back in, I got the y value of my vertex. So the vertex itself is negative 4, comma, negative 17. Now, let's take what we learned on the previous slide, which was the vertex, and let's take this entire equation now. We have f of x is 1/2 x squared plus 4x minus 9, and let's write it in vertex form. We already know the vertex is negative 4, comma, negative 17. Well, if you remember, vertex form also had a leading coefficient. Well, the leading coefficients actually match up. In this case, the leading coefficient is a is 1/2. So our vertex form is f of x equals a times x minus h squared plus k. Remember, h and k are the x and y values of the vertex. So in this case, we get 1/2 times x plus 4 quantity squared minus 17. This is an easier way, in my opinion, of changing forms instead of actually completing the square, is actually knowing how to get the vertex, and then use what you already know about the leading coefficient to simply plug into your formula. Alright. Let's graph this function. F of x is 1/2 x squared plus 4x minus 9. The vertex we know is -4, -17, and the axis of symmetry is x is -4. We know the leading coefficient is positive, so it opens upward. So I can plot my point for my graph for my vertex, and I know it opens upward like this. I also know this point, the y-intercept, 0, -9. If I plot in the points 0, -2, -4, -6, and -8 for x, we get out -9, -15, -17, -15, and -9. Notice in these y values how they repeat themselves. Okay? The reason this happens is because we know this is symmetrical. Remember the axis of symmetry. So if we knew the x-intercept was 0, 9, and we know we have to count over 4 units to the left to get to the axis of symmetry from the y-intercept, if I count over 4 more units, I should hit another point on the graph, because these 2 points are the same distance from the axis of symmetry. So the point 0, -9, and -8, -9 logically both fall on this parabola. Now some of you may be asking, why did I pick even numbers to plug in? Well, I had this little 1/2 out front, so if I picked odd numbers, I'd wind up with fractions, and we don't like dealing with fractions if we don't have to. So I plugged the even numbers in, and that allowed me, when I square an even number, I get another even number, and I didn't have to deal with fractions. Let's see an example of an application. It says a farmer wants to enclose a pen for pigs. He has 100 feet of fencing and wants to use the side of his barn as one side of the rectangular pen. Find the dimensions of the pen that give the maximum area. We'll let W be the width of the pen. Okay? We know we're going to use the side of the barn as one of the sides. And then we have the length, which will parallel the side of the barn. So with 100 feet of fencing to go with on the 3 sides, we get 100 is W plus L plus the other side, the W. So therefore L is 100 minus 2W. We know our formula is area is length times width. So area is 100 minus 2W times W. And if we distribute this, we get area is 100W minus 2W squared. Now this is where we have to conceptually understand this problem. This is the formula for a quadratic equation. We know this is a parabola facing downward. And we know the highest point on a parabola facing downward is the vertex. This is a formula for the area. And therefore, if I'm looking for the maximum area, I'm looking for the highest point on the parabola. So therefore, I'm not necessarily going to solve this equation. I'm actually going to sit there and take this and look for the vertex. I'm going to look for W as negative B over 2A. In this case, it's written a little bit odd. My A is actually -2, and my B is 100. So this is -100 over 2 times -2, which is 25. Therefore, the width is 25, and I defined the length to be 100 minus 2 times the width, so the length is 50. So if I have a width of 25 and a length of 50, that gives me the maximum area for the pen. Let's look at another example. It says a ball is launched with an initial velocity of v0 is 32 feet per second and leaves the boy's hand at an initial height of 6 feet. Write a formula that models the height of the ball after t seconds. This is a standard formula for height of a projectile thrown at a specific height. It's s of t equals -16t squared plus v0t, that's the initial velocity, plus h0, which is the initial height. So s of t in this case is -16t squared plus 32t plus 6. How high is the ball after 2 seconds? Well, s of 2 is -16 times 2 squared plus 32 times 2 plus 6. So it's simply 6 feet high. So after 2 seconds, it's back at the same height with which he launched it from. We can also find the maximum height of the ball. Again, this is an equation of a parabola facing downward. So the maximum height of this projectile is at the vertex. So if I do t is -b over 2a, that's -32 is b over 2 times -16, which is a. So at 1 second. So at 1 second it reaches its highest point. And what is that highest point? Well, we plug in 1 for the time into our function. We get s of 1 is negative 16 times 1 squared plus 32 times 1 plus 6. So 22 feet high is the highest point.